All right, we've got a live stream going, so we'll go ahead and get started with the quiz 2 review. So thank you all for coming. We're primarily just going to be doing a bunch of practice problems to try to help you for the quiz on Thursday. So I have all of the practice quiz problems that we can work through. And then if you have questions on like problems from the homework, we can go over those as well. And I have some additional problems if you want to go over problems that you maybe haven't seen before. So first, I guess we could get started with maybe the practice quiz, since we weren't able to go over that during this past week's discussion. So are there any questions on any of the problems in the practice quiz that you would like to review and go over? Show the last problem of the quiz? Yeah, so problem 6 of the practice quiz, we can certainly go over that. So this one's on an induction. So here's the problem. It's an induction problem. And then for this problem, we're not proving equality, but we're proving less than. So what we have is we have the summation from I equals 1 of 1 over I squared. And we're going to prove that that's less than 2 minus 1 over n for all integers n greater than or equal to 1. So the problem that we're looking at is we're looking at, for those of you who just joined, problem 6 from the practice quiz. And we're going to work through that one. So how do we start an induction problem, right? We always start with a problem statement. So for a problem statement, what we can do, kind of a trick that we've used in this class is we just let's say a sub n represent this summation. And then we let b sub n just represent the right side. And then our problem statement is just really simple. And that's just that a sub n is equal to b sub n. Or excuse me, less than or equal to b sub n. So for the base case, right, for this problem, we're given that n is greater than or equal to 1. So we start with n is equal to 1. So what do we have then? For a1, we have the summation from I equals 1 to 1 of 1 over I squared. And that's just equal to 1. And then for b sub n, that's just 2 minus 1 over 1, which is equal to 1. So thus a1 is equal to b1. And our base case is true. Then we want to state our induction hypothesis. Someone want to state what we should put for the induction hypothesis?
P of n minus 1 is true.
Yeah, we can do that. Yeah, so suppose, yeah, that P of n minus 1 is true for some n greater than or equal to 1. And then now we can move on to the induction step. And since in this case, we assumed P of n minus 1 is true, we're going to prove that P of n is true. Alternatively, you could just assume that P of n is true and prove Pn plus 1 is true. So let me go on to another slide so we have a little bit more space to do this induction step. So for this step, we're going to start with a sub n. And we want to have a string of equalities, and we want to end up with b sub n. So what do we know a sub n is equal to? How could we start off this first part of the proof here?
It's equal to a sub n minus 1 plus 1 over n.
Yeah, plus 1 over n squared. Because remember that we defined a sub n was equal to the sum from I equals 1 to n of 1 over I squared. So we just have the sum of the n minus 1 terms, and then we're just adding in the sum of the nth term. Right, and then from the induction hypothesis, this is where we use the fact that we know that a sub n minus 1 is less than or equal to b sub n minus 1. And that's by the induction hypothesis. And then we were given that we defined b sub n, right? We defined b sub n as 2 minus 1 over n. So b sub n minus 1, we can just substitute in for this formula. That's 2 minus 1 over n minus 1 plus 1 over n squared. And then what do we want to end up with? Well, at the end of this equality, right, we want this equal to or less than, excuse me, we want that to be less than b sub n, which would be 2 minus 1 over n. So we're trying to come up with this formula out of these values that we have here. Does anybody see how we can do that to finish this algebra?
Let's put the fractions in our common denominator. That might make things easier.
Yeah, sure. Yeah, sure. We can try that. So we've got 2 minus n squared over n squared times n minus 1 plus n minus 1 over n squared times n minus 1. So we've got 2 minus, I'll just do plus negative n squared plus n minus 1 all over n squared times n minus 1. And then any ideas from anyone else? How could we simplify this statement? Well, I think we can probably factor right from the top of the expression. How would we? Well, no, that won't factor evenly.
I think we did something wrong. Yeah, I don't think we turn times the right side by n squared or vice versa. No, is that how it's actually supposed to be?
Yeah, because we got this n minus 1 here, and then we got this n squared here.
Yeah, you're right. Factor out a negative from the top, and then I think that's the form we might recognize more.
Sure, we could do a minus n squared minus n plus 1. Yes, here we go. Perfect. Yes, I just wasn't seeing it. Yeah. So then we can factor the top of this expression. That's just n minus 1 times. No, it's not. No, I don't believe that factors evenly. Because the way that factors is just n times n minus 1 plus 1. So we don't get two factors that can help us cancel. Sorry, I'm trying to recall the trick. I know the trick for if we were going to prove this with p of n plus 1, because there's a partial fractions trick that you have to do for this problem, but I hadn't looked at it when we were proving it with p sub n. And I believe that there's a partial fractions trick that we have to do here.
What does the other side of the equation look like right now?
We just have a sub n, right? We're just, because when we do these proofs, we want a string of equalities. So we want to start with this thing on the left, and we want to show that it equals the thing on the right. We don't want to work both sides of the expression at the same time.
So since we're subtracting that fraction, can we like do something like multiply by, oh, I guess we couldn't do that. I'm thinking, because we have that inequality, can we do a trick kind of like the professor did in the last discussion?
Yeah, there's some trick that we need to do here, and I think it involves a partial fractions trick. I believe. I just haven't gone through the direction with p sub n, so I am not. It's just not obvious to me where the trick is. But yes, there's going to be some trick with the less than operator, because we want to end up with a 2 minus 1 over n. So
Yeah, I think on the left side, we also have a 1 over n squared if we make it. At least that's how I did it. If we make it so it's like a sub n minus 1 on the left too.
but we can't make a sub n minus 1 on the left because we're doing the inductive step. And so we're proving that an is equal to bn. So we have to start with a sub n on the left and then get to this point. Well, what could we do here? Well, okay, so one trick we could do is this statement. If we were to add plus 1 over n, right, this expression is clearly larger than this expression because we added something greater than 0 on this side. So that'll allow us to, we can cancel out these two terms. So that'll be equal to 2 plus 1 over n squared. And then I think there's some partial fractions trick. I think what we can do is we can say that this is less than we're gonna get like a I think it'll be like plus there, the negative might be off here. There's a partial fractions trick that I believe you can show that 1 minus n squared is less than 1 over n plus n minus 1 over n. And then if we make that substitution, I apologize. Okay. Sorry, I hadn't gone through this direction for p sub n, but let me make this really clear here. Okay. So we have this expression here. This is just where we got to from proving all the statement directly. Then we can use a partial fractions trick. I believe the partial fractions trick is that we can say that 1 minus n squared is less than 1 over n minus 1 over n. So we'll get a 2 minus 1 over n minus 1 plus 1 over n minus 1 over n, and that'll be equal to 2 minus 1 over n, which is equal to b sub n, which is exactly what we wanted to prove. And I believe it uses this trick.
Yeah, so I was looking at the way I solved this when I solved the quiz earlier. And I don't know. I just want to kind of see if like the way I did it was right.
Sure, yeah, we can talk about it. Yeah, what was your technique?
So I started with p of a of n is less than or equal to b of n. And then I set a of n equal to a of n minus 1.
Something like this?
Plus 1 over n, yeah. And then that's less than, okay, sorry, go ahead.
So that one issue though is we don't know that a sub n is less than or equal to b sub n. So we can't start with that statement, right? Because this is the statement we are asked to prove.
Yeah.
So we can't start with this statement because we don't know that a sub n is less than or equal to b sub n.
Okay. Even if it ends up true at the end, then you'd have to work backwards through every process I did.
Yes, because what you did is you started with this. You started with this thing you assumed to be true, right? You assumed at the start. This is a common mistake, and I see this a lot. So this is really good to kind of go over before the quiz. Um, is the reason why can't we start with this statement? And it's because as soon as you write this statement down and you start working with it, you start with this assumption and then show it to be true, and that doesn't work because you've already assumed what you've wanted to prove is true. So we can't start with assuming that at the start that a sub n is less than or equal to b sub n and then do some algebra to conclude a true statement. We have to start with a sub n on one side and then a string of equalities and then a string to get less than or equal to b sub n.
Okay. So then going backwards through the process I did,
Uh-huh.
I said a sub n minus 1 is less than b sub n minus 1.
Yes, and we get that. That's the induction hypothesis.
Yeah.
So
and
we
then
can
I-
assume this one.
And then I added 1 over n to both sides.
Okay. So then you had that a n minus 1 plus 1 over n is less than or equal to b n.
Yeah. And now I'm seeing I did it wrong because I thought 1 over n. Yeah, never mind.
Okay. Yeah, but no, this was really good. And I was really glad that you brought this up because this is a common issue that I see. So it's really good to go over that. That we have to start like this process here with one side on the left and then string of equalities on the right. If you don't, you can prove a lot of incorrect statements. Like if you can like assume that 1 is equal to 2 and then mess around with both sides and you'll end up with true statements. If you do some tricks, but it's because you start with this assumption. And we can't just start by assuming something is either true or not true. We have to derive that, which is why we can't start with a sub n is less than or equal to b sub n.
We start
so-
with, sorry, one other question.
Sorry, there's just a question in chat. Will we ask a question like this in the quiz? I really don't know partial fractions trick. You may, but it'd be an easy partial fractions trick. We can go through the partial fractions or you could just review partial fractions, right? The way you do partial fractions is you just assume that like 1 minus n squared is equal to like 1 over is equal to sub like I guess the way if you look at the solutions in the practice quiz, the way that the partial fractions trick works is they have like 1 over n times n plus 1 is equal to some x over n plus like some y over n plus 1. And then if you solve for x and y using partial fractions, you can figure out that x is equal to 1 and y is equal to -1. And you can just quickly review that. If it was something on the quiz, just because it was on the practice quiz, it would be an easy partial fractions. And if you can't figure it out on the quiz, something like that, you can just like write some statement next to it. Like, I'm not sure what the partial fractions trick is, but I know that then we could show that this is less than this, and you might earn some partial credit for points like that. So hopefully that answers that question. And then David, we can go back to you for your next question.
Am I good to ask my question?
Yeah.
Okay, sweet. Sorry. So I was just looking at it. I was thinking, could you use a statement like 1 over n squared is less than or equal to 1 over n? And then introduce that into the inequality?
Yeah, this is certainly a true statement because our n is a positive integer. So
yeah, so could you then add that to both sides? Like add that to a of n minus 1 less than or equal to b of n minus 1?
You could, but I would strongly more encourage this direction of the proof where you start, rather than starting with a sub n minus 1 is less than or equal to b sub n minus 1 and trying to add and play with both sides. I strongly encourage this direction where you start from a sub n and then you work your way down. if you mess around with both sides of an equation at the same time, you can sometimes use algebraic expressions that will not end up being correct. It's really easy to make mistakes. Like I'm sure you've seen, there's a very fun, like quote unquote proof where you can prove that like 1 is equal to 0 by messing around with both sides of an equation at the same time, and you'll end up doing something that's like incorrect. So it's just really easy to make mistakes like that, where you do an operation that does not actually then create equality. So I strongly encourage this direction, where you start with one thing, string of equalities, to get to the other. But I don't want to spend too much time on this problem, so we can get to some others. Were there other questions on the practice quiz? First, IH, that stands for induction hypothesis. Great question. Sorry, that was just a shorthand. So any other questions on the practice quiz? And if not, are there any topics that people would like to cover? We could do like a pigeonhole problem, another induction problem, contradiction proof. Are there any topics that people would like to review? Please just type in chat and we'll just go with the majority on that. So somebody asked, do we need a concluding statement for every proof? I don't think it hurts you to add a concluding statement. So like at the end of this proof, we could just say, thus by induction, we have proven A sub n is less than or equal to B sub n for n greater than or equal to 1. And just a simple restatement. It also kind of helps you recall what you were asked to prove if you do this at the end of each of your proofs, just to make sure like you actually proved the thing you thought you did. So I would recommend it. So any questions or concepts anyone wants to go over? Can you go over some tips or tricks from going to induction hypothesis to the induction step? Sometimes not sure what to do. Sure. Let's take a look at another problem. So I have, this is a little induction problem I picked out. It's a little bit different from some of the ones that we've seen. So here you're going to see this like weird pi, big pi symbol. And I don't want that to scare you. We're just using this as a way to express multiplication. So this is like the general product where, sigma is the general summation. So what we're proving here is that like 1 minus 1 over 2 squared times 1 minus 1 over 3 squared times ... 1 over 1 minus n squared is equal to n plus 1 over 2n. Is just converting this statement into just what it represents just with multiplication. And so we can go through this one together. So we've got an induction problem. We're asked induction. Right, so how do we start an induction problem? Well, we start with some problem statement. So let's do the trick where we let A sub n, let's say the expression on the left, so that's just the general product. And then B sub n is equal to n plus 1 over 2n. And then our problem statement is we want to prove that A sub n is equal to B sub n. So now we go to the base case. What's the base case for this problem? What value of n do we start with? Because somebody says 1, close, but not quite in this problem. It often is 1, but it's actually 2. Where's the base case hidden? It's hidden in this I is equal to 2. That means that that's the value, the smallest value we can start with. So the base case is n is equal to 2. So then A sub 2, that's just equal to 1 minus 1 over 2 squared, which is equal to 1 minus 1 over 4, which is 3/4. And B sub 2 is 2 plus 1 over 2 times 2, which is equal to 3/4. So A sub n is equal, or A sub 2 is equal to B sub 2. So our base case is proven. Right now we do the induction hypothesis. So right, the induction hypothesis is we're going to make some assumption about this statement for some value of n. So the induction hypothesis is just what we're stating to be true. So we could either assume that P of n is true or P of n minus 1 is true. In this case, let's just assume that P of n is true for some n greater than or equal to 2. So in other words, we're assuming that A sub n is equal to B sub n for some value of n. And so this is our induction hypothesis. And this is just what we assume to be true, right? And then in the induction, when we go to the induction step, that's where we're actually going to be proving, right, that this statement is true for n plus 1. So the inductive step in this case, right, is we're going to prove that like P of n implies P of n plus 1. We've assumed P of n is true, and now we're going to prove that this is true for the statement P of n plus 1. For the person who asked about tricks from induction hypothesis to the induction step, does this make a little bit more sense? Or were you meaning more in the actual algebra of the inductive step? Did you have a question? Okay, so I'll assume that I didn't see anything in chat. You can keep typing if you want. I can come back to it, but we'll go ahead and move on and start with the inductive step. So let me get to a new page. If I can flip to a new page. There we go. So right, recall, I'll just write this again on this side. We've got A sub n was equal to this, and then B sub n was equal to this. And we're going to prove this. And right, what are we trying to prove? We're trying to prove in this case that A sub n plus 1 is equal to B sub n plus 1. So we start with A sub n plus 1. And then what can we say that this is equal to? Somebody want to volunteer? So right, A sub n is the general product. So what can we do? We can take out the last term just like we do with the general summations. And A sub n plus 1 is just A sub n times 1 minus 1 over n plus 1 squared. Right, we have the product of the n terms, so we can just multiply that by the n plus 1 term. And then there was a question in chat. So they asked in deciding, how do we decide which is easier, going from n to n plus 1 or n minus 1 to n? It's a little bit difficult to know at the start which is easier, and sometimes you don't know which is easier until you've actually tried one of them. Generally, they're both as hard as the other. So I would just start with whatever one is more comfortable with you in doing the problems. It's sometimes hard to tell until you actually start going through the proof which direction is easier, but they generally are both about the same level of difficulty, so it doesn't matter too much. So hopefully that kind of helps. Okay, so here we have, starting with the induction step, right, A sub n plus 1, and then we just broke this up. Are there any questions in this step for how I broke A sub n plus 1 into this?
Yeah, sorry. I don't follow how we got to that step exactly.
Perfect. Okay. Yeah. So let's go through. So we're just using multiplication, right? So we have that A sub n is like 1 minus 1 over 2 squared, 1 minus 1 over 3 squared, right, times 1 minus 1 over n squared.
Okay, yeah, I got it now. I was looking at B of n, not A of n.
Okay. Yeah, then A sub n plus 1 is all the same stuff. You'll have all the same terms, but we're going to have an extra 1 minus 1 over n plus 1 squared. And so that's how we can kind of break this up, because A sub n plus 1 has all the same terms multiplied. So then we're here. What would be the next step in this equation?
Probably plugging in B of n equals A of n.
Yeah, induction hypothesis. This is generally, we want to look for some term with n when we're starting with n plus 1, and we want to always be on the lookout whenever we're doing induction problem. Where can we use the induction hypothesis? Because then once you find that spot, the rest of the proof is mostly just algebra at that point. So here we see we know a sub n is equal to b sub n, so we can replace this with b sub n. And then now we knew what b sub n was. B sub n was equal to n plus 1 over 2n. And then we just do a bunch of algebra. To get the rest. To work out. Oh, that actually. Yeah. And then I don't want to spend too much time on the algebra, but if you go through all the algebra, you'll eventually be able to get this is equal to n plus 2 over 2 times n plus 1, which is exactly what we'd want to prove. I just don't want to spend too much time getting stuck on the algebra so we can get to a few more problems. Awesome. So are there any questions on this one? This was just a little bit different than what you had seen. Instead of doing summations, this one was the product. Don't be scared about this symbol, but just a little bit different than some of the induction problems, but you still should be able to do something like this. So any questions on this one? Awesome. So there was somebody else who asked earlier that I didn't get to when I was going through the practice quiz. Number 1 and number 3 were more difficult. Could we practice solving those? Sure, we could. Would everybody else? We'll just try to do like a majority kind of thing here. Would everybody else want to go through practice problems 1 or 3? Or would you like to try some different problems that are related? And then somebody's saying if we could do a pigeonhole 1 as well. So if everybody just wants to type in chat what problems they'd like to work on, either practice quiz problems 1 and 3, or like a contradiction proof, contrapositive proof, pigeonhole, and we'll try to kind of do a majority vote type of thing. Okay, so you've got contradiction, pigeonhole, pigeonhole. Everyone else who's here, there's like 14 of us. So if you want to type in your opinion, that would be great. Okay, so pigeonhole. Properties of ration. Okay, so we've got quite a bit of, okay. Contradiction, okay. Okay, so I've apologized, David. It doesn't look like a lot of people were voting for that one. If you have more questions on that one, the solutions for the practice quiz are posted. And then if you have more problems, feel free to post on Piazza or come to some office hours before the quiz. But it looks like contradiction and pigeonhole problems seem to have won out. So let's go to this one. Okay, so here's a pigeonhole problem. So we're going to prove using the pigeonhole principle that in a group of 10 people, there are 2 that must have the same number of friends among people in the group. And how are we defining friendship? Well, we're assuming that friendship is mutual. May not be the case in real life, but we're assuming here that if person A is friends with B, then B is also friends with A. Right. And then we're also assuming that you don't count friendship with yourself. Right? You can't be friends with yourself. So only others in the group. And then we've got this hint given as well that can a person in a group have 0 friends while another person in the group has 9 friends. So maybe just take like 30 seconds or so to kind of think about this problem, and then we'll kind of talk about how we could prove something like this with the pigeonhole principle. All right, so hopefully that was enough time. So let's kind of think about how we could start this problem. So first, let's tackle this hint. So does somebody want to explain whether or not this can happen? Can a person in a group have 0 friends while another person in the group has 9 friends? And do they think they see where this might be, maybe would be useful? Okay, so I'll tackle this. So can a person have, so the answer to this is no, right? A person can't have 0 friends in the group while somebody else has 9 friends, right? Why is that the case? Because we said that friendship was mutual. So what this is saying is that if a person has 9 friends, they're friends with everybody in the group, right? Because we can't be friends with yourself, so there's 9 other people, they're friends with everybody in the group. So that means that everybody in the group must have at least 1 friend, right? So there can't be somebody that has 0 friends. So what this hint is kind of telling us is that we might have to consider 2 cases. One where somebody in the group has 0 friends, and another possible case where somebody in the group is friends with everybody. So let's break this down into some cases. So let's do case 1. Someone has 0 friends. In the group. So if somebody has 0 friends, what are the possible number of friends that people in the group could have? So then people could either have 0, 1, 2, up to 8 friends. Is kind of what we're saying in this case. These are all the possibilities. So now we need to start thinking about how does this work? How is this working with the pigeonhole? If we're in this case, somebody has 0 friends. Does somebody want to suggest like what might our boxes be here, and what might our objects be for this problem?
I'm thinking boxes are number of friends you have, and the objects are the people, because 0 through 8 is 9 options, and so you're gonna have a duplicate.
Yeah, that's perfect. That is a perfect explanation and idea. And we can even go through just a little bit more in depth about like how could we figure this out? Well, we know that we have, right, m for the pigeonhole, right, we have these kind of general equations. We have n times n plus 1 is the number of objects. We have one box containing at least n plus 1 objects. And then we have n boxes. Right, so for this problem, if we're kind of thinking about objects as people, then we know that m times n plus 1 is equal to 10. We have 10 total people that we want to put into these boxes. And then we want to prove that 2 of them have the same number of friends. So we know that m plus 1 is equal to 2. This implies that m is equal to 1. And that implies also that n is equal to 9 if we just plug in those values to these equations. So we know we need, since n is equal to 9, that's the number of boxes. And that's just a little bit more if you're sometimes struggling on the Pigeonhole and you want to kind of think about how do I figure out the number of boxes and stuff, then this is kind of the technique you can go through. But what David brought up was a perfect idea and saw kind of straight away that, well, if we have these are the possible number of friends and we have 9 options, we can just label those as the boxes. So label boxes based on the number of friends. A person has. Right, so then there are 9 boxes because there's 9 total options. You could have 0 through 8 friends since we already eliminated that you can't have 9 friends. So there's 9 boxes, 10 people. And then by the Pigeonhole principle, I'll just abbreviate it PHP. 1 box has to have 2 people. So that's kind of case 1. Are there any questions on this case? For how we figured out this works with the Pigeonhole principle. Any questions? All right, so then we can go through case 2, and case 2 nearly identical. So case 2, we just assumed that someone in the group has 9 friends. Right, so then each person has either 1, 2, 3 through 9 friends. We've got 9 options again, so we just label boxes based on the number of friends. So then we place 10 objects in 9 boxes. So 1 box contains 2 objects. Thus, by the Pigeonhole principle, or it contains 2 objects by the Pigeonhole principle. So those 2 people have the same number of friends. In either case. So we're done with this proof. Are there any questions on this one? Or in general for Pigeonhole? So this one is a little bit tricky. It's a little bit different than maybe some of the ones that we've seen. The trick to this problem was really figuring out this kind of hint. And then it's just kind of a standard application of the Pigeonhole principle. All right, if there's no questions, then, oh, wait, somebody says, so can you use more logical reasoning than mathematical reasoning with Pigeonhole principle? Yeah, for example, this problem, right, is not like, we don't have any like values or equations or formulas, right? We just have groups of people and we're proving things about friendships. These are not strong mathematical like definitions. So this is perfectly fine to kind of use more logical reasoning. And sometimes that happens with the Pigeonhole principle. And that's because we have to explain in words how we construct our boxes, right? And how we're labeling objects and stuff to put into boxes. So on the test, you want to be explicit in that. You want to say, like, by the Pigeonhole principle, we're going to create these, we're going to label boxes like this. We're going to put objects in like this, right? You want to be descriptive and explain what you're doing to label those boxes and to get this set up. So then when you apply the pigeonhole principle, it's kind of obvious what is happening. So yeah, for like a problem like this, this would be more logical. For example, there's some of the ones that we've done like in class, for example, where we're proving like that given 7 numbers, you can prove that 2 of them have a sum or difference of 11. So that one is more mathematical reasoning because you're using properties about the integers and such alongside pigeonhole principle. Or on the homework, where you had to prove that given 5 integers, the sum of squares of 3 of them would be a multiple of 3. You're going to have more mathematical reasoning on that one. But the one thing is, don't be afraid to write sentences out and stuff in your proofs, right? Not everything can be expressed in mathematical statements and stuff, so don't be afraid to just like write out sentences explaining your reasoning and stuff. So hopefully that kind of makes sense. Awesome. So if there's no other questions then on pigeonhole, we can move on to contradiction, which seems to be the next largest area of questions. So let's take a look at this problem. So we're going to prove using contradiction that the sum of 2 odd perfect squares is not a perfect square. And then we're going to use this fact for this proof, that no perfect square can have the form 4k plus 2. We're not going to use, like in the homework, we had a stronger statement here, but for this problem, we're not going to use that stronger statement. We're just using this hint here. So does somebody want to kind of start us off? We've got a problem. We're doing contradiction. So how do we start a contradiction proof?
We say that we have 2 odd perfect squares that sum to a not perfect square.
Yeah. So by contradiction, we're going to assume that this statement is actually true, right? We're going to assume, yes, that the sum of 2, that there exists 2 perfect odd squares.
So if they're an odd perfect square, does that mean that they were like, wait, never mind.
That are a perfect square. So this is how we start with contradiction, right? We're asked to prove that this thing can't happen. So we'll assume that, let's assume that it could happen. So somebody says yes. Yes, Alec, you are correct. We did say something like that about perfect squares as well, but we're not going to use that for this. We're just going to use only this hint for this problem. So what does it mean? And so we've got, this is what we're assuming for the sake of contradiction. So let's give these things names. So let's let a squared and b squared, b and c, and be odd perfect squares. So if they're odd perfect squares, that means that like a squared is equal to 2m plus 1, and like b squared is equal to 2n plus 1 for some m and n in z. And then, so Alec, you actually have the right idea here. So they're suggesting, could we write these just as I did, 2k plus 1 or 2k plus 1 squared? And that is something we would like to do, but I'm going to try to do this like we do, like you're going to on the quiz, where you're not going to know that's the case, right? If you want to use that statement, we're going to have to prove that we can do that. In other words, we would need to prove if a squared is odd, then a is odd. And then David, you had a question?
Yeah, I was just wondering if the squares were odd or the if A was odd or A squared was odd, but I think you just answered that.
Oh, yes, yes, A squared, yes. Yeah, when we say an odd perfect square, we're meaning that A squared is odd, but it also happens to be the case that this is true, that A would also be odd, but we would need to prove that that's the case. And that's just how it'll be on the test, right? You'll be able to use the division theorem, the Pidgeonal principle, as something else, I believe, and then everything else, if you want to use on the test, you'll have to prove if it's not already given to you.
We can use that kind of statement on homeworks, though, right?
Yeah, I don't think we took any points off for a statement like that on the homework.
Cool.
I think, yes. So let's try to prove this, because it would be really nice in this proof to be able to use the fact that A is odd. So then, and just a little bit of reasoning why, if we look at A squared plus B squared right now, we're going to have 2m plus 1 plus 2n plus 1. And our hint tells us we want to look at something for 4k plus 2. And this is just 2mn plus 2. But if we could look at these values squared, we're going to have a lot of 4s, and we're going to be able to get something of the form 4k plus 2. Because then we'd have 4m squared plus 4m plus 1 plus 4n squared plus 4n plus 1. So that might lead us down. Oh, yes, the fundamental theorem of arithmetic. Yes, I believe that was the other thing that you can use. So yeah, good job. That one, I couldn't remember that one. So that's kind of where we're headed. So it'd be really nice if we could use the fact that A was odd. So let's try to go down that proof. Does somebody have any suggestion? Right, we've gone over
Contrapositive.
Yes, contrapositive. That's the way we prove the statement. We went over the one for even in class. Good idea. So let's write the contrapositive of the statement. So if A is even, then A squared is even. Right, contrapositive, we negate P and Q and flip.
Also, if anyone's wondering, my reasoning for going there first is that I would rather not have to write A squared equals 3k plus 1 and then have to take a root and do weird stuff with that. I'd rather be able to start with A being something rather than A squared being something.
Yes, that is perfect reasoning. And yes, it's always better to start with like A, and then we can conclude using, if we know something about A, then we can use that for something about A squared. But yes, taking roots is really difficult, and we don't know a lot about properties of taking roots giving us like integer values. So this is certainly the better direction. So yes, perfect reasoning to get to the contrapositive. So this is the contrapositive. So let's prove it. If A is even, then we let A be equal to like 2k, where k is an integer, and that's by the definition of even. So then A squared is equal to 2k squared, 4k squared, which is equal to 2 times 2k squared, which is equal to 2m. And why can we say this? What's the special property we talk a lot about that allows us to rewrite values as other integers?
Closure.
Yeah, so this is by closure of multiplication for integers. Then this is even by definition. And that kind of concludes the proof. So thus, we proved the contrapositive, so thus the original statement is true. So thus is A squared is odd, then A is odd. And that kind of concludes this little proof we needed to do in order for us to prove this larger statement here. So now we've done this proof. Were there any questions on this kind of small proof here? If A squared is odd, then A is odd. On anything we did here. Awesome. So then we can continue with the rest of the proof then. So since now we know that since a squared and b squared are odd, then a and b are odd. So a is equal to, I think I'm running out of variables here. 2x plus 1, and b is equal to 2y plus 1, where x and y are in Z. And then now we can just kind of take a look at what a squared plus b squared is, because we wanted to prove that the sum of two odd perfect squares is not an odd perfect square. There's not a perfect square at all. So we can take a look at this, and we just expand these using the definition of what we said for a and b. So we'll get 4x squared plus 4x plus 1 plus 4y squared plus 4y plus 1. If we factor 4 out, this will be x squared plus x plus y squared plus y plus 2, which is equal to 4l plus 2, where L is equal to this, the stuff on the inside. And L is an integer by closure of the integers under multiplication and division. Or excuse me, multiplication and addition.
Do we have to write it all that way, or can we just say closure by then like a dot, comma, and then a plus?
Yeah, you could, as long as it's clear that you're talking about that you state that you're using this under multiplication and addition, and you mentioned for the integers. So as long as so if you do a shorthand, to try to save time on the quiz, that's fine. As long as it's just clear.
You have
like
to say closure of integers.
Yeah, because certain things aren't closed, right? Or we at least haven't shown that in class, right? For example, you could prove that, like, say the rationals are closed under addition and such, but we haven't talked about that in class.
Well,
so that's what we're telling you about integers.
So the domain statement of the problem doesn't just imply that. Like on this thing, all of our numbers are integers.
Yes, we just wanted to be clear that you're talking about like the integers here. So why can we say that this is an integer? Well, we're using closure under integers for these two operations.
I'm just being pedantic because I'm concerned about my homework, but thanks.
Okay, yeah. Yeah, no problem. And then now we can use the fact, right, that no perfect squares are the form 4k plus 2. We've got something of that form. So by the hint, this is not of the form of a perfect square. Well, excuse by the hint, no perfect squares are of this form.
We never have to prove hints, right? We can just take them as given.
It depends. Generally, yes. Sometimes the hints will tell you should use this thing. So then you should like use that. So for example, like if this hint was instead maybe something phrased like use, like on a different problem, we might say like use the division theorem and consider cases like this. Well, if we're telling you to use this thing, you should use that thing. So you should start your proof off by the division theorem. Let's, and then consider cases like this. And if we're telling you like you may use this fact, then yeah, you don't need to prove this. And it would be explicit on a test. You would know if we wanted you to prove. If a hint, we were telling you like maybe as a hint, maybe for this problem we could tell you like prove a squared is odd. If a squared is odd, then a is odd. So that'd be a hint, like directing you should do this proof. You just have to look at the phrasing of the hint, but it'd be obvious if you're asked to prove something. Otherwise, you can generally just accept these as facts that you can use in the proof, but make sure to state them. Like, don't just like end your proof here and just like, don't stop the proof here and get to here and then be like done. Right. Use the hint, which tells us that, oh, it's of this form, thus this is not a perfect square. Right, so thus a squared plus b squared is not a perfect square. Right, don't just stop the proof here because the hint tells us that it's not a perfect square. You need to use the hint to explain that. So are there any questions about this?
So I remember the book used a couple examples of like talking about the counter hypothesis. Do we need to say anything like that in the proof, like that no counter examples exist because we've shown the contradiction?
I mean, you could certainly state it like that, right? But it's fine enough just to state like that our hypothesis is true, right? Because we found like we found a contradiction, right? This is no perfect squares are this form, and this is a contradiction to our assumption. Right, we assumed that we got a perfect square and we didn't. So thus a squared plus b squared is not a perfect square. So, and I mean, you could restate if you wanted to, you could restate. So thus, like the sum of two odd perfect squares. Is not a perfect square. Like this, which is nearly the same thing as saying thus no counterexample exists, right? So the original statement's true. Yeah, really good question. Then make sure, like I did, I nearly forgot it. Make sure to point out where you get a contradiction. If you're doing a contradiction proof, you should make it clear where the contradiction is, right? This is our contradiction. We assumed that a squared plus b squared was an odd perfect square, right? We assumed that there exists two odd perfect squares that have a sum of a perfect square. And this was the contradiction that we ended up with.
This is a little silly, but I have seen it in the book. They always use an exclamation point when they find a contradiction.
Oh, that's just kind of a fun thing to do. I think they're just doing it for like, it's, oh, here's the surprise contradiction. You know, also if you're gonna, yeah, so you don't have to do that. As a side note for this problem, we actually proved that there does not exist a right triangle with integer sides whose base legs are odd. This is just kind of expanding that sometimes our proofs, you know, have different interpretations, right? And so this is one interpretation of this proof because we proved stuff about the sum of squares. And if you take like later courses in math or something, you can do fun proofs like this, which you may not think are geometric, but actually are really related to geometry. So that was just a little aside.
Is there a definition of even and odd for non-integers, or is it just not mean anything?
It just doesn't, I think it just doesn't mean anything. In all of the math that I know, it does not mean anything to talk about like rational numbers being even or odd. Generally, when we talk about even or odd, we're just talking about the integers. So are there any last minute questions? We're a little bit over, but are there any last minute questions? For quiz 2.
What's the fundamental theorem of arithmetic again?
Oh, sorry. Yeah, I did miss that. So the fundamental theorem of arithmetic, that is that every integer is a product of primes. is the fundamental theorem.
A unique product of primes, right?
A unique product of primes. Yeah, it can be written as a product of primes in one and only one way, ignoring reordering. So like, 8 is equal to, well, that's not a very good example. 10 is equal to 5 times 2 and 2 times 5, but these are unique primes.
But they can be repeated.
Yes, the primes can be repeated. The way you can write them is unique. The primes in them are not unique, right? 8 is equal to 2 cubed. There's a unique product of primes, namely 2 times 2 times 2, but the primes can be repeated.
But not 1, right? Besides 1?
1's not a prime number.
But any number can be written as a product of primes, but 1 can.
Oh, but 1 and 0.
Gotcha.
If I don't know quite how it's phrased in the book, we can take a look, but I believe that's generally given as the kind of like, except it's sometimes phrased in and then there's a caveat for like odd numbers as well, generally. So it looks like it's on page 129, every integer greater than 1. Okay, so they just ignore anything else. So every integer greater than 1 can be expressed as the product of a list of prime numbers. Any other questions? Oh, somebody asked, why isn't 1 a prime number? You can take a so the reason why is because there's a lot of so 1 was a prime number. Back in like the 1920s, they considered it a prime number, but it turns out that a lot of things that are true about the primes are not true about 1. So they just threw 1 out, because a lot of proofs, they would like prove things about the prime numbers that were true for every prime number except 1. So they just took 1 out of the definition of a prime number. So it's just how we define it. We just define the prime numbers to like exclude the number 1, because it turns out 1 has kind of weird properties. Not very interesting properties, but it turns out compared to the rest of the primes, there's exceptions. Any other questions for the quiz? There'll be a review session again tomorrow during Nancy's office hours that you can attend as well. That'll also be live streamed on YouTube if you can't make the time and want to watch it later. And then there will still be office hours on Wednesday. So Dr. Cohen and I believe Ben will have office hours. So there's still lots of time to get help if you have questions, and feel free to kind of post on Piazza as well if you get stuck on anything. The homework will be returned to you before the quiz. We're hoping to get that done really soon. To be able to go through that as well before the quiz. Oh, somebody, okay, awesome. So if there's no more questions then we'll all go. The rest of the slides that I have are posted in the quiz review session. So there's a couple other problems that I selected. You can go through those for practice as well. So thank you.